Hi guys, and welcome to this lecture. Now we're starting to get into something that's a little more complicated with our understanding of how things work, and then later on in other lectures when we get to some calculations. However, what we're looking at now is resistors in parallel. So up until this point we've just been dealing with series circuits, which means we get a power supply and a resistor and another resistor, say like that. That would be our most basic type of series circuit. And we found with this type of circuit that all of the electrons would leave the negative terminal. They must go through this resistor and they must go through that resistor as well. So if this was 1K and this was 1K, we found out that the total resistance is going to be 1K plus 1K, which is 2K. But if we were to get rid of that resistor, we're now just left with 1K. So every time you put resistors in series, or the more that you put in series, the bigger the resistance is, or the greater the resistance is. You may recall that, let's just get rid of this, we could actually simplify our circuits down to just this. And we'd call that RT, which is our total resistance. Sometimes I've also called it the equivalent resistance, which means if we were to get all of the resistors in our circuit and replace it with just one resistor, what value would that resistor be? Well, in the case of this circuit, that one resistor would be 2K. If we were to have something like, let's get rid of that, just missed that one. If we were to have, say, 2K and 3K, and we were to replace those two resistors with one resistor that does the same job, that would be a single 5K ohm resistor. Or what about, I was about to say something else. What if we had a circuit like this? 1, 2, 3, 4 resistors in series, like that. And this was a 1.2K, and this was a 3K, and I should put ohms here. And this one was a 2K ohm resistor, and this was a, let's make it a 2.8K ohm resistor. Well, in this case we've got 1.2 plus 3K, that's going to give us 4.2 plus another 2. That gives us 6.2 plus 2.8 would be 8.2, so this would give us a total of 9K ohms. So that means we can replace all of that with a single resistor that is 9K ohms. The amount of current we get in flowing in this circuit would be identical to the amount of current flowing in here, as long as we had the same power supply. So I realize I'm going through series again here, but I just want to make sure that we have this grounding so that when we get to parallel, we kind of have something there already as a baseline for which to work with. Okay, so let's now have a look at a circuit simulator. Here's a simple one resistor series circuit. We have a look, there's 10 volt power supply. All of that voltage is going to be across the 1K resistor. In fact, when I click on this resistor, you can see over here the voltage drop VD is 10 volts because there's no other component in the circuit to grab any more voltage. 10 volts divided by 1K, the amount of current in the circuit is 10 milliamps. And because it's a series circuit, it doesn't matter where we click, it's always going to be 10 milliamps. What if we got another resistor though? We put it in series. What's going to happen to the total resistance? Well, all the electrons have to go through the first 1K resistor and the second 1K resistor, so now we have a total of 2K. We have 10 volts, which is now across 2K. In fact, let's repeat that circuit. Let's get rid of that. Let's make the equivalent circuit. And unfortunately, this doesn't have the best auto routing for the wires. Let's replace that with a 2K. That circuit there is identical to that in terms of voltage, resistance, and current. How much current is going to be here? Well, it's 10 volts divided by 2K. We'll get 5 milliamps. 10 volts, 2K, 5 milliamps, exactly the same. This is our equivalent or total resistance compared to this one. Now, one other thing before we get to parallel. In series, the current, just got a message then, the current is all the same through everything. The current through this one is going to be 5 milliamps. You can see over here, the right hand side. The current through this one is 5 milliamps. That's because the electrons only have one particular path that they can go through. Now, if we have 5 milliamps through here, and that is a 1K resistor. Yes, the calculator is what I want. 5 milliamps, 5 exponential negative 3. That's the current going through it, multiplied by a 1K ohm resistor. We should have 5 volts across there. Same for this one. 5 milliamps, 1K should be 5 volts. Do we have that? Yes, we've got 5 here, and we've got 5 over here. So a series resistor circuit, or a series circuit with any components in it, will form what's known as a voltage divider, and we've discussed this before, which means that 10 volts is going to divide itself amongst however many components there are. 5 volts plus 5 volts gives us 10 volts. What if this was a different value? What if this was 2K? Well, you'll still have that plus that equaling 10, it's just that now the 2K will get more. Instead of having 5 volts, the 2K has about 6.67 volts. The 1K, being the smaller resistor, gets the smaller voltage, 3.33. So you add those two together, you get 10 volts. A series circuit, the current is the same through every component, so remember that. However, the voltage will divide itself up. Now that we're going to do parallel, it's the complete opposite of that. So what is a parallel circuit? Let's start with a power supply, a single resistor like that. What do we have there? 10 volts, and this was 1K, and we found out there was 10 milliamps. That was our current. Now, when we connect something in parallel, the way to do that is you must connect the top of both resistors to the same point, and let's just make this a 1K as well, and you must connect the bottom to the same point as well. That is how you connect something in parallel. Think of parallel lines. If I was to draw a line like that, a parallel line, or a line in parallel with that, would be straight across it like that as well. Resistors, you connect the top of each of them together, the bottom of each of them together. We now say that they are in parallel. So something interesting happens when you do that, and it's best if we look at the circuit simulator to do that. Here's our power supply, here's our resistor. Let's connect up this, and again the wires are not auto routing for me very well. It's alright, we can work with that. So there's that circuit. Oop, right there. Let's just change this to 10 volts because that's what we're dealing with. And let's make this 1K, which it already is. 10 volts divided by 1K, how much current is there? 10 milliamps, 10 milliamps. It's everywhere 10 milliamps. Now, let's add another one. Hopefully you'll be able to see that we're now giving the electrons a bit of a choice. The electrons start from the negative terminal. They were only going up that way, if you recall, because that was the only way they could possibly go. But when we connect another resistor in parallel, they now have a choice. They can go, well, I'm going to go down this way, and I might go up this way. Or they might go this way. They actually split off, and you can actually see it in this circuit because you've got the little red, sorry, not red, you've got the little yellow squares going around the place to indicate the flow of electrons. Alright, so have a look at this. In a series circuit, we said that the current through every component is the same, because the electrons only have a one path to follow. But the voltage, the 10 volts, would split up and divide itself amongst those components. Now let's just swap that completely. This time, voltage will be the same across every component instead of current being the same. And then the current is the thing that splits up. So let's have a look at that. Notice where this resistor is connected to. The top of it goes straight to the positive of the power supply. The bottom of it goes straight to the negative of the power supply. Therefore, we have a complete short circuit straight to the bottom, a complete short circuit straight to the top. Therefore, we have 10 volts across that resistor, and we can see that over here, 10 volts. What about this other resistor? Well, the top of that one goes straight to the positive terminal. The bottom of that one goes straight to the negative terminal. It's identical to this one. It's connected exactly the same. It also has 10 volts. Anytime you connect something in parallel, the voltage across each one is exactly the same. If we were to grab a multimeter and measure these, you'd find there'd be 10 volts. Anywhere, if you put the red lead anywhere up here on any one of these lines, and the black lead on any one of these lines, you'll come up with 10 volts everywhere. Okay, So voltage is the same across every component. But what's happening to current? Well, current starts out from the negative, it chucks a right, and then it splits up. So if you imagine, yeah, I'll bring this in now. Let's go to the supermarket analogy that I was going to bring up later. So let's picture that you're at a supermarket. You're doing your shopping because you're hungry, you need to eat. Here you are. You're coming through here, and all these little yellow things indicate different shoppers. Let's say there's only one supermarket checkout open. Every single shopper has to go through that one checkout. Therefore, the amount of current that we have indicates how fast we're getting the customers through. Now let's say that let's say the 1K resistor indicates someone who's really good at their job. I mean, they're pushing through these groceries really quick. If we were to replace that with a 2K resistor, that indicates someone who's a bit of a trainee. They're pretty new to the job, they're putting them through pretty slow. The current is now 5 milliamps compared to 10. Okay, we'll come back to that though. Now, how can we speed this up without changing that person at that checkout? Well, what if we open up another checkout? Let's do that. So that means we have like these parallel checkouts going on right here. So all these shoppers coming through, and now they've got a choice. They go, well, I might go through this aisle, this lane, or I might go through this lane. In this case, we've got 1K and 1K. That indicates that the checkout operator, they're just as fast as each other. There's 10 volts across there, therefore the amount of current is 10 milliamps. There's 10 volts across there, and again it's 1K, so we again get 10 milliamps. So if there's 10 through there, and there's 10 through there, how much must we have started with before we got to the split up point? Well, it's going to be 10 plus 10, which is 20. So we have all these shoppers coming through. They now have a choice of where they can check out, this one or this one. They're going to get through them both the same because the checkout operators are both 1K. So they split up, we get twice as many people through in the same amount of time. Now notice at this point here, and by the way, this little dot down here, we call that a node. Wherever current is going to split up or join back together, we call it a node. Here we start off with all of the current, we get to this node, it splits up, 10 and 10. At this node, hopefully you can see they're joining back together. 10 milliamps, 10 milliamps. What are we going to get on the outside of that node? 20 milliamps. So a parallel circuit, the voltage of each component is the same because they're all connected straight to the power supply. They all get 10 volts in this case. However, we've now got multiple paths that current can take, so current can actually split up. Because the current can split up, we divide up the current. So just as we call a series circuit a voltage divider, we can call a parallel circuit a current divider, because that's what it does, divides it up. Okay, let's do this for a little example. Let's make this a 2K resistor. So this indicates we've got a really fast worker here, they know what they're doing. This guy's a bit slower, he's a trainee. However, the total amount of current is still going to be greater than if we just had one aisle open, one checkout. Because this guy is always going to have 10 volts across him, he's always going to be 1K, he'll always have 10 milliamps going through. If we then open up another checkout, even if the checkout is slow, overall we've still increased the rate of people getting through there. Even if we got, I don't know, someone who really doesn't know what they're doing, they're putting through, I don't even know who to say who's working here. Someone who is on their first day of the job and they're like a 10K ohm resistor, really slow. In fact, they're so slow you can hardly see the yellow dots. However, we still get the 10 milliamps going through there. We still get the 5 milliamps going through there because it's 10 volts divided by 2K. And we now get an extra 1 milliamp going through here. So 10 plus 5 plus 1 is 16. Now let's say we train this guy up and he gets a lot faster, we get 1K there, and then this guy, they really fast track him and they train him up, so here's 1K. 10 volts, 1K, 10 milliamps. 10 volts across here, 1K, 10 milliamps. 10 volts across here, 1K, 10 milliamps. How much did we start with? 30. So that 30 comes along here, 10 goes up that way. How much comes down this way? Well, 30 minus 10, we're left with 20. 20 milliamps goes this way. It splits up again. 10 goes that way. How much are we left with? 10. Then 10 comes through here. That 10 groups with this 10 at this node here. So what do we get? 10 plus 10 gives us 20 again. 20 plus 10. So 20 coming through there from these two guys, plus 10 coming from this single guy. We're back to 30. Alright, lots of talking there. But so no real calculations, or nothing too intense at this stage, because we're going to get to that into the next lecture. But key points I want you to take from this. Whenever you put resistors in series, you increase the total resistance. So if we were to replace, I'm just going to go back here for a second. If we were to replace, I'm just going to move that out the way. In fact, now I'm going to delete that. So here's my series circuit again. There we go, 1 and 2. 1K there, 1K there. If we were to replace that with a single resistor and still have the same amount of total resistance, it would be 2K. So anytime you put resistors together in series, you increase the resistance. RT goes up. What would happen to the total current then? Well, that must go down. More resistance, less current. And then from there, we divide the voltage. So this will get a portion of the power supply, this will get a portion. Current through each component is the same. What about the parallel circuit? So here's a 1K resistor here in parallel with another 1K ohm resistor. So what we found in this case is whenever you put them in parallel, and we'll do the calculations for this in the next lecture, but you'll find that the direct opposite happens compared to series. The total resistance actually goes down. So if we were to replace that circuit with a single resistor, and this will make sense when we get to the calculations, so don't worry at the moment, it would actually, for that circuit, it would actually look like 500 ohms. Resistance goes down. What therefore happens to total current? Well, it goes up. And that's exactly what we found. So get rid of that, get rid of that. 10 volts, 1K, 10 milliamps. You put a resistor in parallel with that, you've now opened up an extra current path, so there's more choices for current to go through, or there is a choice now. Therefore, we've gone from 10 milliamps total current to 20 milliamps total current. Let's just for fun, let's do the calculation. So if there's 10 volts total voltage, and there's 20 milliamps total current, so 10 volts total voltage divided by 20 exponential negative 3 for 20 milliamps, it actually looks like 500 ohms, just as I showed there before. So resistance total goes down in parallel, total current therefore goes up, and it divides the current. So a parallel circuit, you can call a current divider. Okay, so that's just a little bit of an introduction to it. In the next lecture, we're going to pull out our calculators a bit more, do some calculations, and hopefully all this stuff will sink in a little bit more. Thank you for watching, guys.